think we are live. Let's just wait one moment for the stream to catch up.
Sure.
Hopefully there's no echo. Okay. I think we should start, yeah.
Let's do it.
All right. Hello everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim. Just wait one moment for the stream to catch up. Oh shoot, I'm hearing some echo. Oh,
yeah, from you.
What the heck?
Told you it was your fault.
We should start now.
Let's do it.
All right. Hello everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim. Let me try this. Let me try to catch up. Oh shoot, I'm hearing some echo. Oh,
yeah, from you.
What the heck?
Told you it was your fault.
We should start now.
Let's do it.
All right. Let's try this again. Hello everyone. Welcome to today's brand new episode. Okay, I'll wait a little bit. Maybe should be good now. Or maybe there won't be a sound for me. Don't understand why there's echo.
I'm still
Or
hearing
maybe
echo.
there won't be a sound for me. Don't understand why there's echo.
I'm still
Or
hearing
maybe there won't be a sound for me. Don't understand why there's echo.
I'm still hearing
Maybe there won't be a sound for me.
Are you guys also hearing like 45 seconds?
Okay, for some, I think it should be good now. I think. Zoom is uncooperative with this new setting, but I've stopped sharing Zoom. Should be good now.
I'm still hearing echo.
Really? I don't hear one.
I don't hear one, yeah. Do you? Really? Sahil? Maybe you just need to mute yours. I mean, like, just, well.
Okay.
Maybe you just need to.
Uh-oh.
That is frustrating. We tested this.
Okay, let's go. I won't be able to see the stream, but let's go.
Okay. All right, let's try this again. We can try to cut it out a little later. All right. Well, anyway, hello everyone. Welcome to today's Quadcast. Today's Quadcast episode. I am your host Tim, and let's get right into it.
Mikey. And there's no more echo.
And Sahil, welcome everybody. Apologies for all the technical difficulties. We're back. Welcome to brand new exciting episode of Corecast. If you haven't already joined our Discord channel, and if you watch us on YouTube, we do this every 5 p.m. Pacific, 8 p.m. Eastern.
There's still echo, I guess.
There's still an echo?
Okay, this is... Maybe this is better. But maybe there will be no sound from me. Can you, Sahil, say something?
Thanks.
Yikes. Okay, let me remove this. Okay, that's unfortunate. Okay. Well, this is unexpected difficulties.
Only your voice is okay, Tim.
Still, why would that be the case? Yeah, that's very strange. Maybe if I remove this, it's a little bit of black magic. It should be multi-output device. Is it still having a problem? Or is there no sound from you guys? It should be good if Sahil sounds okay. Mikey sound, yeah. This is a slight mystery. Wait, Sahil, there's no sound for Mikey? Or maybe there just is no sound.
Yeah.
Okay, yeah. Maybe this is good now.
Doesn't seem like anyone can hear me.
I changed a few settings now. It's a little bit of a black magic because there's so many sound audio source, and apparently the screen also comes with audio source. Maybe that was a mistake.
Oh. But no one can hear me, huh?
I think it's
Mikey's
good now.
okay. Yeah, we're good. We're good.
Yeah, it's good now. This streaming software has problems. That was not. Okay. Well, despite all this, let's get started with some delay. Should we start again?
Yeah, let's do it. Let's do it, Tim. Start us off. Let's go.
Boy. All right. Hello once again, everyone. Welcome to Corecast. I am Tim, your host.
Now, Mikey.
This is Sahil. Welcome, everybody, to a brand new, exciting episode of Corecast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we try to do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to it. So without further ado, let's get to it. So, Tim and Mikey, I remember when I was taking introductory physics, learned all about these like various different constants, like speed of light, gravitational constant, you know, even in mathematics, constants of like 1, 2, 3, 4, 5, pi, the number e, all that stuff. And, you know, and we were talking about how like some of these constants may not actually be constant. So can we like break down first, you know, when you first learn in high school, like why certain things are called fundamental constants before we discuss like maybe they're not so constant after all? I guess Mikey.
Yeah, like so I just wanted to distinguish between like the kind of two constants you described. Like, you know, if you talk about things like the gravitational constant, right? Like versus something like the number pi. I wouldn't consider those things constants in the same sense because, oh gosh, I don't know, getting kind of like philosophical, but like the number 3.1415, whatever, like that's we sort of define that as a fixed number. When we talk about constants, we usually mean things that don't change or can't change with time. So yeah, if you think about the number pi, it's sort of like defined to be that number. So it can't change unless you change the definition. Although I guess you could imagine a universe where suddenly the ratio of the circumference to the diameter of a circle somehow changes to something other than 3.1415. But
I would say,
yeah, I just think it's different than like the gravitational constants, so the constants we talk about in physics.
Yeah, I would say mathematical constants, I think, are defined, you know, without experimentation. I think mathematicians would argue that those numbers are defined logically without reference to any particular real objects in the universe. So even if in our universe the ratios of circumference to the diameter changes, you know, we wouldn't change pi. We would just have some reason to be like, hey, look, it's not the same thing as pi. But something like the speed of light, for example, I think has an operational meaning. It's like, hey, if you follow at least colloquially speaking, particle of light, this is how much it will cover as ground given 1 second, right? So those have some distinctions. Like you could imagine a hypothetical universe where that number, how fast light moves, that could change. You can kind of imagine it almost, but I guess it's impossible to imagine logic where the idea of pi would change, because it's just axiomatic. It just is true. So I think we should distinguish those two, right?
Yeah, so it seems like there's two different kinds of constants, those that can be measured and those that are defined within the mathematical language itself. And the ones defined in the mathematical language aren't necessarily measured, they're just defined and like computed in some fashion.
Right.
That's in a certain sense.
They are. I mean, they are. I don't know. I keep going. They are kind of similar, right? Because you can measure the ratio of the circumference to the diameter of a circle, and you can come up with the number 3.14. I guess the main thing is like if that changed, then we would be really, really shocked. These other things, we just think they're constant because we've measured them millions of times, and we get the same exact answer every single time. But there's no principle that we know of for why these things should never change.
So I guess now coming back to constants that you can measure like physically, I mean, yeah, you are right, Mikey, that you could like draw circles, a bunch of circles and diameters of the circles, and then measure the ratio of those two things, the circumference to the diameter, and keep computing pi, and hopefully you get the same answer. But for things like speed of light, universal gravitational constant, and so on and so forth, I guess like are these what we would call fundamental constants, or like what would, I mean, I guess like could I construct like maybe like the mass of an electron and call that a fundamental constant, for instance?
I would say yes. Although I guess, yeah, we're going to get into some controversial viewpoints about this, but right, like if you encounter a rock and it's so heavy that no one can move it, you consider that rock constant until you develop the technology to, move it.
Yeah, I would say, like once we make that distinction, like the number pi 3.14, there sort of is like a logical meaning behind it, right? There are mathematical formulas that dictates what it should be. However, for let's say the speed of light, it's just what it's measured to be, right? If let's say the speed of light was 10% smaller, I doubt anyone would have bat an eye, be like, hey, well, why the heck is the speed of light a tiny bit lower versus what the value is, right? And in some sense, and also the value of the speed of light actually isn't all that meaningful if you really think about it. So the numerical value is, let's say, roughly 3 times 10 to the 8 meter per second, something like that. And imagining, it's the U.S. You don't like the metric system. You can convert that to miles per hour. I don't know how many that is. You can even convert to how many times it goes around the Earth per second, right? It's 11 times. So like in terms of the numerical number, like which is it? Is it 3 times 10 to the 8, or is it 11 point sometimes per second around the Earth? Like the actual numerical value isn't meaningful as opposed to the actual numerical value of pi, which is meaningful. So I think there's a distinction there.
You would be pretty surprised if you saw light starting to slow down one day, though.
Yeah. So I would say when we talk about the speed of light, we actually talking about two separate concepts. Yeah. So I would say first, there is this thing that's roughly 3.0 times 10 to the 8 meters per second. There's this number. Let's not call it the speed of light. Let's call that number some number, and in physics we use c. Yeah, and it happens to be that the speed of light matches that number, and you can argue that conceptually that number exists independent of whether light exists or not. So that number itself is a concept, right? But the actual speed of light itself, it didn't have to be exactly that number. So it's possible to actually break that concept down into two pieces, right? One is there exists some number that has the unit of speed. The numerical value is, something like 3 times 10 to the 8th meter per second. And then there's a separate concept of the speed at which light moves in. In our universe, they happen to coincide. But those are actually two separate concepts.
Yeah, that's kind of semantic, though, right? Yeah, it's true that there's other particles that also travel at the speed of light, and we just call it the speed of light because light was the first thing we ever found that travels at that speed. But yeah, for sure, that number has an existence that's independent from light. But it is actually kind of similar to pi, though, if you think about it, right? Because pi is the ratio of the circumference to the diameter of a circle. And this number, c, 300 million meters per second, that's like the ratio of like space to time in terms of like its hyperbolic structure. Right?
But I think if we talk about it in that language, now we disentangle these two concepts, then it starts to make sense, right? Like the concept c in physics is a theoretical construct, very much similar to the idea of pi, kind of independent of the circle. We believe that the universe has certain symmetries, like Einstein proposed, and that space and time are one and the same thing. Then this number c is kind of like a conversion factor, like how much space, how much time does it take to get certain amount of space. I know it's kind of vague. But somehow the speed of light travels at the maximum speed, so it's kind of getting the best exchange rate there. So it moves at this upper bound, this conceptual framework, right? But I think even though the speed of light could change, like in water, in air, speed of light is a little different. The concept c actually would be I guess as close to a constant as possible in physics. Yeah.
I guess I'm still trying to understand. So you were talking about speed of light. We talked about it's a conversion between space and time. At the same time, though, I mean, like, so when you talk about pi being meaningful, it seems like pi doesn't have any units. Pi is not like 3.1415 whatever meters or seconds or something like that. So it seems like the original thought that you were giving is an artifact of the units that you're choosing. But what if you were to
unit?
What?
It's 3.14 circumferences per diameter, right?
I mean, you could view it as radians, but now we're kind of getting it into the weeds here in some sense. I kind of
but it is a unit. It's a is it less arbitrary? I don't know. I'm kind of
in some sense. Well, the difference is that you're constraining like the mathematical structure of it. For instance, like you're saying that there exists this circle, this perfect circle that has this property of it. Otherwise, we wouldn't call it a circle. Like for an ellipse, you wouldn't say like I don't know, loosely speaking, diameter of an ellipse is like, and the circumference of an ellipse or the perimeter of an ellipse, that ratio shares like pi or something like that.
Yeah, I mean, right, it depends on the shape, right? So as soon as you start to stretch the circle, the ratio of the circumference to diameter changes. So you could say, that, okay, that's like a different kind of pi for that particular shape. And in our universe, you could kind of think about it the same way, like this this number that we choose to measure in meters per second. I mean, I guess you could choose to measure it in terms of like universe lengths per universe time. And it'd be closer to like radians, I guess. But.
Yeah, but I think this brings home a point that the speed of light as a constant is very arbitrary if you think about it. Like, why did we choose meter per second? Meter is really just some cobbled up concept. It's around, we humans decide what a meter is. We humans decide what a second is ticking, and they roughly correspond to some, I don't know, average, like the definition of a second is some atomic clock sitting somewhere, right? And then the definition of a meter, I don't know, is there like a meter stick somewhere? I don't know, like how many atoms stacked together? I think they define the meter by the speed of light, right? So if you think about it, ultimately the speed of light that we measure, the value, is actually, to really define it, we have to gather some atomic clock, some electrons moving around, look at that physical process, and look at a meter. I don't know, I somehow compare that to the motion of light particles, and then go through some complicated formula, and then we derive the speed of light, operationally. And when you think of it this way, it doesn't feel like it's so sacred of a kind of like a sacred fundamental constant anymore, those numbers.
Wait, sorry, like this might be a silly question, but like, do you happen to know what the speed of light is in units of Planck length per Planck time?
Well, I mean, it's just one, right? At the end.
Oh yeah, right. Yeah.
Yeah. So that's why in particle physics, the speed of light is one, and then when you talk about how fast your car is moving, it just so happens that the speed at which our car moves is very, very small compared to the speed of light. It's like 10 to the negative 8 or something, or even smaller. So.
Yeah. So okay. So I want to kind of take a step back because I feel right now we might be going on like a little bit of a tangent. My one question is like, okay, so we've talked about the speed of light is arbitrary. One question that kind of was the basis of this episode is the speed of light actually changing? Or like, how do I put that question in the context of what we just talked about? If I come to you as a high school student and ask you, hey, I learned about this concept called the speed of light. It measures how fast light moves. It's based on measurement. I've seen a graph that like the measurements are kind of like they oscillate, they're not exactly flat. Is the speed of light constant? Or if it is, how do you know that? And if it isn't, how do you know that?
Yeah. So
wait, oscillations? What kind of oscillations are you talking about?
I think just errors he's talking about,
Oh, okay.
Yeah. So I think that has two parts, right? So first of all, what are you measuring? Okay. But let's ignore the measurement part for the moment. Yeah. Because depending on how the apparatus works, your measurement might differ one way or another. The question is, which concept are we talking about that's varying? Yeah. Mm-hmm. So, and there are multiple possibilities. First of all, are we talking about the concept of the conversion between space and time changing? Okay. So that's possible. But then we don't quite believe that to be the case, because we believe Einstein postulated that the universe has a symmetry. There's a relationship between space and time, and that is fixed, because space is time, and that doesn't matter where you are. So this conversion rate should remain the same, right? So I think from that perspective, theoretically, I don't think we would believe that notion will change. Of course, it could change, and if it were to change, it would be groundbreaking in the way that the Einstein's belief of the symmetry between space and time is completely wrong. There is no such symmetry, meaning that the conversion rate could vary. So that's one possibility. The other possibility is the actual speed at which light travels, because that's not the same concept anymore. Now, if light was to be able to slow down, it's possible, but that means that the way light moves has to go through some mechanism, and maybe that mechanism is changing while still the relationship between space and time is not changing. So Einstein could, if that were true, Einstein probably is still correct, but it's just that there's some additional physics affecting how light moves, right? So those are kind of like a two different take on, what it means for the speed of light to be constant.
So I want to ask a question about the second thing that you mentioned, and then kind of bring us back to the first point that you mentioned. Second point, say the speed of light is changing, but not the constraint or the ratio, or I don't know what to call it, the relation between space and time as given by Einstein. Let's say that was correct, but the speed of light itself is changing. does that mean that all like the measurement of the universe's age would be different? Like all our cosmology be different if that were true?
Yes, that could possibly affect things. Basically, in order for that to be true, you would go through the normal particle physics argument. You would say that, hey, light actually has an additional interaction, changing the way it moves. Yeah.
Mm-hmm. That makes sense.
Yeah, and then throughout the universe, yeah, the way light moves could theoretically be different.
How would one know? Actually, Tim, what evidence would I need to present to you to show you speed of light has changed for you to be like solidly convinced, okay, there's something here?
Wait, the speed of light or the space-time ratio?
The speed at which light moves. Sorry, the speed at which light moves.
Oh, you just have to measure it and then show that it's different, right?
Yeah, I think one possibility is probably the cause of that will be coming from electromagnetism being a little different in different places in the universe.
Mm-hmm.
And then I would imagine you would see, for example, hydrogen in a distant galaxy could behave quite differently because hydrogen is governed by electromagnetism. And you could see variations of that throughout different parts of the different directions in our universe. Although we don't see that, but if we really see some drastic, variations of that, yeah, that could be a plausibility.
Yeah, the easier way would be to just, shine a light and then time how long it takes to reach and then show that it's different. Then I'd be convinced.
Right, but then those change, but rapid changes of the speed of light is probably not possible because we've done so many experiments.
But
yeah.
I mean, all cosmological measurements are consistent with the speed of light being constant. But I think what Sahil meant was, he could do a demonstration to show you that the speed of light was changing. I mean, it's just very direct, right? We're just talking about the speed of a certain object.
Mm.
Yeah. So now I want to go to the first point you mentioned, Tim, which is a little bit, maybe a little more tricky, showing Einstein is wrong through like this relationship between space and time not holding. So I guess like, what would that mean if that were not true? Like, what would happen? I guess like if that relationship did not actually hold.
Yeah. So I would say that I think there's some reason to suspect that the relation between space and time is probably maybe not even as sacred as we thought it was.
Oh.
So that relationship could just be kind of a happenstance, right? So a good analogy is this: if you, for example, if you take a magnet, the magnet has a north pole and a south pole.
Mm-hmm.
And if you look at, let's say, like a really nice looking magnet, you see a very intricate magnetic field around it. And you might ask the question, what a beautiful, symmetric object of the magnet. Where did it came to be? But if you zoom in into a magnet, you find that the magnet actually has a lot of substructure, right? There are little domains inside the magnet. There are little tiny magnets in it, and somehow they randomly distribute themselves to create this macroscopic magnetic shape of a magnetic field. Yeah. It's sort of like a symmetric object. It's plausible that our space-time maybe will be similar to a structure that's like that. For example, string theory or whatever. That, the fabric of space-time could be made of something else. So the appearance of space and time could be emergent. And thus, the conversion factor would just be like, kind of like an apparent conversion. And maybe really deep down, there is no fundamental way to have that conversion. So if that was true, yeah, you could say that the speed of light as a relationship between space and time in Einstein's theory could break down, actually.
Yeah, but I mean, it still holds along. So you're just saying that if you look very, very, very closely, like super microscopically, you might see that light is actually doing something else, and it just kind of looks like it's traveling in a smooth path at the speed of light. But I think the question Sahil was asking more, and I'm curious about this too. Could you ever perceive that this ratio of space to time is changing without, aside from, of course, measuring the speed of light and seeing that it's changing? Like, is it even really possible to separate these two?
I think it is possible, but when I say changing, I don't mean just that. Oh, somehow the exchange rate is different. I think I mean that the concept doesn't even apply anymore. Like there is no space and time in which for this exchange to happen, I would say.
Yeah, but assuming that there is a space and time, like macroscopically.
Yeah, I think you might see some deviation. You might start to see some deviation when you zoom in. And then the moment you try to measure that, let's say, and you see that, hey, well, the concept of space and time doesn't really apply anymore. Of course, I don't know exactly what that looks like. It's quite speculative. I think nobody does. But fundamentally, we believe that space-time is also emergent, I think. And that would be true, I think.
So what you're saying is that there's some reason to believe, which we won't get into right now, that space and time itself is emergent. They're not truly fundamental. And if that's the case, then this relationship between space and time through the speed of light, or c as it's called in the literature, is actually more of an emergent phenomenon, not actually like quote unquote fundamental. Is that correct, Tim?
Yeah, I think that's a plausibility, and I personally would. I think I would believe that. I would be inclined to believe that. Yeah, and it would just mean that the speed of at least this this number, is kind of just an accident. Like, maybe in our universe it's 3 times 10 to the 8 meter per second. It could have been 10% lower. Maybe it could have been 10% higher. We wouldn't have thrown a fit. We wouldn't be like, oh, what the heck? Why is it a little higher? No, lower. We wouldn't even be that much confused if it was slightly different. So if that,
I feel like we're getting a little off topic though, right? Because I guess we started out using the word fundamental constants, and now we're sort of talking about like fundamental versus constant. You're saying that the speed of light might not be fundamental, but it would still be constant, right?
I guess you can argue that it's approximately constant in our universe if you don't zoom in. If you buy this story, but you could argue that if you go to different universes, it might not be the same anymore. So in that logic, then maybe it's not so constant after all. But of course, you can't necessarily travel to different universes. So
I thought when we're talking about constants, we're talking about whether or not something can change with time in our universe. Like, certainly if you take a powerful enough hammer and you just smash space-time with it, like, with Planckian amounts of energy, then, probably you will see, in such a crazy distorted space-time, you would actually, the speed of light would be changing, right? Because there would be so many ripples in the Einsteinian fabric. But does that mean it's not constant?
Yeah, I think there's this popular belief that, a lot of these numbers that we see, that we plug in an equation, the speed of light, for example, or the Newton's constant, somehow these are like sacred numbers that, I don't know, something wrote down. It's like a perfect design or something, that it's completely immutable, right? But now, I think if you dig deeper into it, these numbers could just be like an accident, and it could have been different, and it's maybe not as sacred as we thought it was, and maybe in the multiverse they could actually be different. Yeah, so now this concept of fundamental constant, I feel like it becomes a little murkier.
So
I agree, not fundamental, but I don't know, I haven't heard any arguments for why these things aren't constants. Heard arguments for why they're not fundamental, and I buy that.
I guess going back to Mikey's question, can you have these constants or constants in quotes be time varying? Like they just change with time?
I think practically speaking, given the way our universe is, probably not in our universe. Maybe even if it varies in time, it'll be extraordinarily slowly, right? Like not in our lifetime. But hypothetically, could it totally change in like a bazillion years? Maybe, right? When all the galaxies are gone, black holes take over. Maybe the cosmology will be dominated by quantum fluctuations once again. Then maybe these so-called constants could change once again.
No, there's no reason to believe that. The only way to make them change would be to develop a microscopic surgical procedure to change the shape of space and time at a microscopic level, and then sure, then you could change it, and then it would be similar to what you said about different values in the different parts of the multiverse, where the fabric might have a different shape or twist to it. But I don't think we should lead the audience to believe that there's any reason to think that trillions of years in the future these things will be changed. I mean, if anything, the speed of light is as we know it, is defined in a flat background, and the universe is probably going to stick to that. So
I guess like one question I have is, does this also apply to other constants and also dimensionless constants as well? Same train of thought.
I feel like the only way to discuss this is like not in terms of are these things constant, but like how surprised would you be if they changed? Like pi would be like super surprised. Like if I found out that someone could change that number, it'd be like, whoa, that's like, okay, then I'll just like kill myself. But speed of light is up there too. But like, things like you mentioned, like the mass of the electron, that one is almost certainly subject to change depending on, even the temperature of the room.
Yeah, I would say most constants actually. If you dig into the fundamental physics of it, at least personally, and also probably a lot of physicists would argue that they would, it wouldn't be that surprising if you see those values can go up and down one way versus another. So in principle,
you mean like the mass of the electron, right?
Exactly, yeah. Like maybe it doesn't change practically, like in our universe, or you wait 1,000 years, you run experiments that again and again. Yeah, that's not the massive electron is not going to change. I can probably guarantee you that. But it doesn't mean that it cannot be changed in principle. And I think in physics, we generally believe that many of these so-called constants in our universe could, in principle, change. Like our universe could have been produced with some of these numbers slightly tweaked.
Or even in our universe, it could change the conditions and measure different values for these things. I think there's basically like the big three, right? So aside from mathematical constants, I guess that we argued are more conceptual, the three that would be most surprising to see changing would be what? The gravitational constant, speed of light, and Planck's constant. Did I miss one?
I think that's about it. And some of them...
That's like the big three.
Yeah. And many of these constants, because they have units, it's we always have these ambiguity. Like, are you talking about the concept, or are you actually talking about the value? Like the speed of light actually is, the rate at which the speed moves. But every one of these constants, like the Planck's constant, the gravitational constant, there's a theoretical aspect that tells you what it relates to. There's also an experimental aspect where it says, hey, look, this number relates to, for example, how planets move, right? Or how quantum physics fluctuates. But those two can actually be separated, right? And those, and Mikey was saying, yeah, there are two layers of concept for each of these constants.
Mm-hmm. That makes sense. I guess like I had a question, now I lost it. I guess like kind of going on this theme of multiple universes, there's one sort of question. So you mentioned like different universes can have different constants per se. Is there any like comment that you have about like, I guess maybe they could be changing in other universes, or would they also be constant in other universes, just take on different values? Or what's kind of the theoretical underpinnings of that? If that question has been answered.
So I think when you mentioned this, it almost seems like there are two different scenarios, right? It's like, oh, either they can change wildly, or there are multiple universes, each of them having different constants, but they stay the same in their own respective universe, right? Mm-hmm. And I think in reality those two concepts merge, like, because observationally we don't see these constants fluctuating violently. So what happened is when universe is created, there's a mechanism for which these numbers could change. And then there's also a process in which the universe gets a lot bigger, so it gets stretched out. So these numbers become relatively constant in a large universe, because like imagine like a tiny patch of universe with certain values. If it gets stretched out really large into an entire universe, then of course the entire universe will see a constant value. I think that's this idea is I think what most physicists believe to be happening if these constants do in fact are changing. So they are changing, but then they get stretched out, so it stay consistent in different universes.
And you also mentioned a very interesting example with magnetism, or like a magnet. You have these different domains and they all point in like specific directions, and then together you get this magnet that like has this magnetic field as if it's like in one direction. Could you maybe take that analogy, extrapolate it further, and think of it as like if you believe in like multiple universes, like our universe has like several constants that point in a particular direction. As you like go to different universes, they like change over space in some sense.
I don't know, maybe I can give like a specific example. So like one of the biggest motivators for this multiverse idea comes from string theory. And in string theory, the idea for how you explain these constants is that if you look really, really closely, like you zoom in super, super closely into space and time, you see that it's actually not flat, but it's got a bunch of crinkles in it. And those crinkles, kind of determine how fast light moves through it. But in the neighboring universe, it could be crinkled into some other configuration, and then light would, or if there's something like light in that universe, it would travel with some different perceived speed. I think you can even calculate the energy it would take to crinkle space from one configuration to another configuration, and it would probably be, astronomical. But one day when we've ascended to the level of gods, then who knows? We might be able to pull something like that off.
Yeah. I mean, there have been physical theories that even suggest that, like imagine the universe next to us, some of the constants could be drastically different. I mean, they're not constants anymore. Then there could be a transition zone where the constants, changes from one value to the next. And these would be what we call domain walls, or defects in the space-time. And those regions where those constants would change would carry a tremendous amount of energy. And you could see perhaps like a lot of stars, galaxy forming, or some even more strange phenomena. They could be particles annihilating, sending cosmic rays in our directions. So that's definitely in the realms of plausibility. Although we have never seen such thing, but it has been proposed.
Mm-hmm. That makes sense. I guess now, kind of taking a giant step back, we've explored the different constants, but I guess like Tim and Mikey, like in your own personal speculative opinion, like in seeking the ultimate theory of physics, are these constants actually in there, or are they just like artifacts of like what we currently see and like our limits of what we can I guess do theoretically at the moment?
I think it's always best to assume that everything is an artifact of, because there's so much we haven't seen. There's so much distance we haven't zoomed into, and we don't know what's there. And every time we thought something was constant, when we encountered rocks that seemed so big or mountains that couldn't be moved until someone invents dynamite. So in that spirit, I think it's just a safe assumption. But I would still be on the side of calling them constants because, I think they are fundamental descriptions of the particular universe that we live in. And I don't think they're likely to change over time. But yeah, I agree with Tim that, conceptually, these things are probably all artifacts.
Yeah, I think my opinion probably maybe a little more extreme, but I think I think the more we study physics, the more we realize that a lot of the stuff that happens in our universe kind of is just kind of an accident, right? Like our universe is governed by all these numbers. If these numbers are not just like a fact of life, just like the distance between the Earth and the Sun, it's just or the size of the Earth is just some numerical value. If these didn't happen by accident, you have to try to answer the question. Well, there are these knobs in our universe. Who's dialing them? Somebody's controlling them, and then you go to this territory. You might invoke deities or whatever, which is, I think, a lot of which doesn't really conform to the scientific mindset. So I think that's why a lot of physicists will take the default position that says, hey, look, sure, we have a lot of these dials in our universe, these knobs that can turn constants, so-called constant up and down. But really, there is a natural process to dial these knobs. And the natural contender is this idea of multiverse. And once we invoke that, I think, I think it's the Copernicus view of universe again, right? We used to think the Earth is special, 4 seasons, we have the sun is special. The more we study the universe, the Earth is very much not special anymore. The solar system is very much not special anymore. And if you take that to the extreme, you would argue that our universe is also not so special anymore. And all these constants are just kind of like, okay, they just are what they are.
Were you going to say something, Mikey?
Nope.
Okay. All right. So we're almost at time. I wanted to give you guys a chance to leave the audience with any parting words.
I would just like to part by saying that I will be shocked if the speed of light or Planck's constant or the gravitational constant changes, but nothing else would shock me.
Yeah, and I would say that, and the title came from me, I would say that maybe nature probably doesn't really have any constants. At least the way we think of, like, sacred mathematical truth, like pi. I don't think we have anything like that. Physics is...
Well, no, really what you're saying is there might be an infinite number of constants.
Possibly. And we just happen to hop onto one of them. None of them is special in any way.
They're still constants, though. Until next time.
Yes. All right. Well, on that note, I want to thank you for joining us, and we'll see you all next week.
All right. See you next week.
Bye.
Bye-bye.